طيب اوكي، هون خلصنا فكرة انه exergonic and endergonic reactions when coupled they can be addressed with one adjective. Like you can consider them either endergonic or exergonic. What does that mean? That means if they're exergonic together, the net free energy is minus. That means it's exergonic. That means that the exergonic part or reaction provides more or equal or more energy than what the endergonic reaction needs. So in this case we look at here عندنا glutamic acid. For glutamic acid to become glutamine, it needs energy. Like for ammonia to be connected with glutamic acid, needs energy. This that's why the free energy is positive. We explained it like free energy before, but just was more theoretical, and this is the practical aspect. This is the like empirical aspect. So this reaction on its own, it's endergonic. It needs 3.4 kilojoule per mole. So now that's the role of ATP in driving chemical reactions. Now here, the breaking of ATP on its own, they consider it on its own, to provide to end up with ADP and inorganic phosphate group. This provides 7.3, which is in the minus. Now, if you separate these reactions, you will look at the phosphate group here, which is this phosphate group that the ATP will provide, will link up to the glutamic acid, and it will become phosphorylated intermediate, which is phosphorylated glutamic acid. Now, this phosphorylated glutamic acid, this phosphorylated intermediate, is less stable, is more reactive. They use a lot of words like less, and more. It has more free energy, which will be used in order to drive the endergonic reaction that needs 3.4. Now the ammonia here will replace the phosphate group in the intermediate phosphorylated product, and we'll end up with glutamine and these end results. That's the whole idea here. Now, if the other two objectives or tasks that ATP is needed for is transport and mechanical work. Now, transport is moving one molecule through or from one spot to another against its spontaneous or exergonic pathway. Mechanical work is like muscle works or celiac thumping, whatever they called it. Now, ATP, now the crucial aspect of the idea here is that ATP hydrolysis causes changes, that's the word, in the proteins, in the shapes. Now, shapes and binding affinities of proteins. Binding affinities. So if they have an affinity to bind with one thing, after the changes to the shapes, they will be more prone to connect to something that they're not usually connected to. Okay. So this can occur. This can occur either by directly, which is called again phosphorylation, as shown for a membrane protein, carrying out active transport of a solute, and or indirectly by a non-covalent binding of ATP and its hydraulic products, as in the case for motor proteins that moving vesicles, okay, motor proteins and cells. Like that's this third example of mechanical work, and move vesicles here along the cytoskeletal tracks in the cells. So if we look at it, transport proteins here with ATP. Now, what does ATP do? ATP phosphorylates. Now, here, it phosphorylates. What does that mean? That means it delivers a phosphate group and to the transport protein. This is the transport protein, and causing a shape change that allows transport. So that's very evident. That's very obvious. And here's the organic group that's discharged after the transportation is conducted. Now, as for mechanical work, now ATP binds non-covalently, as in weakly, to these motor proteins within the cell. Then, after it binds to these motor proteins, they are hydrolyzed, causing a shape change that walks the protein forward. Like here are, like, for instance, here are the feet of the motor proteins. They are connected to the cytoskeleton of the cell. The ATP binds to, let's say, this one here, and once it binds to it, this no longer becomes like it loses its affinity to this point in the cytoskeleton. It will become like kind of liberated, free to choose a different one, so it will be more prone to connect to here. Now the motor protein is already attached to the vesicle, so once it moves like this, now another ATP will connect to this, it will move like this, and the crawling will happen. Now it's need all of this. It's the details of that are not like crucial. Now oops. Now let's look here. Now we have this is the ATP cycle. Energy is released by breakdown reaction, which is catabolism in the cell is used to phosphorylate ADP. Okay. In order to regenerate, in order to regenerate ATP. Now, chemical protein or chemical potential energy stored in ATP drives most. And this is an important idea here. Chemical potential energy. So, ATP itself is like a person who climbed the top of a ledge, and if the person falls, the potential energy that this person has, potential kinetic energy, will be released, and it will drive his fall, because like a mixture of gravity and whatnot. Now, in terms of chemical potential energy, the ATP has a chemical potential energy that is provided by the breakdown reactions in the cell, which turns ADP, which has low chemical potential energy, to ATP. Now, if we look at the details of this, we have ATP and water, which is the ATP hydrolysis. The ATP hydrolysis always releases ADP here and inorganic phosphate group, which yields energy. This is now energy for cellular work. This energy is needed for all endogenous reactions within the cell, which consumes energy. The amount of energy that we need here should be more, like, let's say, minus than what the work is positive. Now, what do we do with the ADP and the inorganic phosphate group that results? Now, we need energy in order to regenerate the ATP by, this is called the ATP synthesis. That's it. No more details here, so we'll just skip it till we actually see. Now, the regeneration of ATP. An organism at work uses ATP continuously, but ATP is a renewable source that can be regenerated by the addition of phosphate. Now, the free energy required to phosphorylate ADP. Now, where does it come from? This, because phosphorylating ADP is an endogenous reaction. It needs energy. Now, where does it come from? It comes from the exergonic breakdown reaction, which is catabolism in the cell. This shuttling of inorganic phosphate and energy is called the ATP cycle. Now, so they use the word shuttle, like to shuttle the shuttling, as in they carry the inorganic phosphate and energy through, like, the train track or something, in order to couple them and regenerate ATP. It couples the cell's energy yielding, look here, couples the cell's energy yielding processes to the energy consuming ones. That's an idea we covered before, the coupling of exergonic and endogenous reaction, so that there's never equilibrium, because that's the death of the cell. Now, the ATP cycle proceeds at an astonishing pace. For example, a working muscle cell recycles its entire pool, wow, of ATP in less than a minute. That turnover represents 10 million molecules of ATP consumed and regenerated. That's per second, per cell. If ATP could not be regenerated by the phosphorylation of ATP, humans could use up nearly their body weight in ATP each day. Because both directions of a reversible process cannot be downhill, the regeneration of ATP from ATP is necessarily endergonic, logically. Notice the positive here, which is exactly what ATP provides in energy, which is exactly what ADP needs as energy to become it. I mean, that's just basic logic. Now, since ATP formation rate is not spontaneous, free energy must be spent to make it occur. Catabolic pathways, especially cellular respiration, provides, we're going to study it later on, provides the energy for the endergonic process of making ATP. Plants also use light energy to produce ATP. Thus, the ATP cycle is a key player in bioenergetics, functioning as a revolving door through which energy passes during its transfer from catabolic to anabolic pathways. Okay, now as a concept check, how does ATP typically ATP typically transfer energy from an exergonic to an endergonic reaction in the cell? Yeah, sure. Whatever, we studied that. Which combination has more free energy? Glutamic acid plus ammonia plus ATP, or glutamine plus ADP has more free energy. Overall, this is an exergonic reaction, meaning it will result in a minus. So this has more. Which combination? So this has more. I would say that the end result has more free energy because it's minus, but let's just look at the. So here they're saying I get it. So what they're saying is that here, if we consider it like this, free energy final minus free energy initial. It's an exergonic reaction. It's going to be minus, meaning that the initial has more energy. What is passive or active transport? Which figure? This figure? Where? Figure 611A. This 611A. This is an active. It's an yeah, whatever. Now, what is the role of enzymes in? What is it? Okay. Enzymes speed up metabolic reactions by, that's a very important concept, by lowering energy barriers. What does that mean? What's an energy barrier? An energy barrier is the threshold above which the energy provided will be equal or more than the energy needed. If a reaction needs 7 kilocalorie and the energy provided is 6, now the energy barrier of 7 is will prevent the thing from happening. Now the laws of thermodynamics tell us what will and will not happen under given conditions, but say nothing about the rate of these processes. Nice, and that's a very important concept. The rate of these processes. A spontaneous chemical reaction occurs without any requirement for outside energy, but it may occur so slowly that it is imperceptible. For example, even though the hydrolysis of sucrose, the sugar, to glucose and fructose is exergonic, occurring spontaneously with the release of free energy, which is this. A solution of sucrose dissolved in a sterile water will sit for years at room temperature without appreciable hydrolysis. However, if we add a small amount of the enzyme sucrase now to the solution, then all the sucrose may be hydrolyzed within seconds. Now, here sucrose can sit for years without appreciable hydrolysis. You add sucrose and then it happens like in mere seconds. So how does it work? Like the concept of an enzyme as a catalyst. Now it speeds up the reaction without being consumed. That's a very important concept. Without being consumed by the reaction. That's why it's not a normal reactant. It's an enzyme. It's a catalyst. In this chapter, for enzymes that are proteins. Not all enzymes are proteins, but some RNA molecules like ribozymes can function as enzymes. These can be discussed later. Now, without regulation by enzymes, chemical traffic through the pathways of metabolism may become terribly congested because many chemical reactions would take such a long time. In the next sections, we'll see why spontaneous reactions can be slow and how does enzymes do that, like accelerate the process. Now, the activation energy barrier. Now, every chemical reaction between molecules involve both bond breaking and bond forming. For example, the hydrolysis of sucrose involves breaking the bond between glucose and fructose. And one of the bonds of a water molecule, and then forming two new bonds which are shown above, which gives as in the glucose here and fructose, they take bonds OH from water and H from water. Okay, now changing one molecule to another generally involves contorting the starting molecule into a highly unstable state. That's an idea, like an important idea. decreasing the stability of a molecule makes it more reactive before the reaction can proceed. Now, this contortion can be compared to the bending of a metal keyring when you pry it open to add a new key. Okay, the keyring is highly unstable in its opened form, but returns to a stable state once the key is threaded all the way into the ring. To reach the contorted state where bonds can change, reactant molecules must absorb energy from their surrounding. When the new bonds of the product molecules form, energy is released as heat, and the molecules return to stable shapes with lower energy. Yeah, okay, that's second law of thermodynamics. The initial investment of energy for starting a reaction, the energy required to contort the reactant molecules so the bonds can break, is known as free energy of activation or activation energy. E A, energy of activation. Now we can think of activation energy as the amount of energy needed to push the reactant to the top of an energy barrier so that the downhill part of the reaction can begin. Activation energy is often supplied by heat in the form of thermal energy that the reactant molecules absorb from the surroundings. The absorption of thermal energy accelerates the reactant molecules so they collide more. Oh, that's a good idea. They collide more often and more forcefully. It also agitates, and that's a good idea, the atoms within the molecules, making the breakage of bonds more likely. Look how you can notice how they're introducing ideas like more likely, colliding more often and more forcefully, which increases the chance, which increases the possibility that the reaction will happen. So the reaction will definitely happen, but increasing the chance by agitating, by destabilizing the atoms, the molecules at atomic level, accelerates the reaction. Not only making it sometimes possible instead of impossible, but also making it happen more often. So if we think, like at first, if we think of the reaction as needing 7 energy, we need a source of 7 energy for it to happen. However, if we think of the of 100 reactions, they need 700 energy. Now, if we think of those 100 reactions as one block, as one entity, thus the activation energy for the whole block needs to be provided by something in order for the reaction as a block. And then if we apply that energy to each separate molecule, it doesn't just allow the reaction to happen, but it also accelerates the process of it, which is what the enzyme does. Now, when the molecules have absorbed enough energy for the bonds to break, the reactions are in an unstable condition known as the transition state. Now, this graph, that's just the reference to this whole paragraph is just an interpretation or an application of the second law of thermodynamics, which is when heat is released or absorbed, entropy in the system changes, but generally increases in the release of heat. Now, heat is there, as molecules strive to be, as the system strives to become more at equilibrium, it'll absorb the components in the system will absorb the heat. Now, the molecules themselves will have a higher entropy, making them less stable, uh, less at equilibrium. And in their pursuit of equilibrium, they will accelerate, speed up their reactions that will, as an end result, produce the products that we need. And the enzyme works as a catalyst, like as a component in this whole idea of entropy. Like, it's the enzyme is an agent of entropy. Anyway, let's go for more specifics. The graphs are the energy changes for a hypothetical exergonic reaction that swaps portions of the reactions. Okay, the activation of the reactants are represented by the uphill portion of the graph, in which the free energy content of the reactant molecules is, it's too much words. I feel like this is a word salad. At the summit, when energy equivalent to energy of activation has been absorbed, the reactions are in transition state. They are activated and their bonds can be broken. Okay. As the atoms then settle into their new, more stable bonding arrangements, energy is released to the surrounding. Okay. This corresponds to the downhill part of the curve, which shows the loss of free energy by the molecules. The overall decrease in free energy means that the energy of activation is repaid with dividends, as the formation of new bonds releases more energy than was invested in the breaking of old bonds. And that's how we get energy. Basically, that's the whole idea. Now, the reaction shown in figure this is exergonic. It occurs spontaneously. So, delta free energy is minus. Now, however, the activation energy provides a barrier that determines the rate of the reaction. Now, this activation energy working as a barrier to determine the rate of the reaction. How does it do that? The reaction must absorb enough energy to reach the top of the activation energy barrier before the reaction can occur. So the reaction can occur, but there is this the reaction can occur and is occurring. But for it to occur at a perceptible, appreciable value, and so that it can be useful, so that it can provide its use, the rate of the reaction determined by this activation energy that the reaction needs to acquire from its surrounding, will sort of unleash this reaction at an appreciable level. For some reactions, it's modest enough that even at room temperature, there is sufficient thermal energy for many of the reactants molecules to reach transition state in a short time. Now, in most cases, however, energy of activity is so high and the transition state is reached so rarely that the reaction will hardly proceed at all. In these cases, the reaction will occur at a noticeable rate only if the energy is procured or is provided, usually by heat. Now, for example, the reaction of gasoline and oxygen is exergonic and will occur spontaneously, but energy is required for the molecules to reach the transition state. Only when the spark plugs fire in an automobile engine can there be explosive release of energy that pushes the pistons. Without spark, no. Now, how enzyme speeds up reactions? Proteins, DNA, and other complex cellular molecules are rich in free energy and have the potential to decompose spontaneously. Now, that is the laws of thermodynamics favor their breakdown. These molecules only persist because at temperatures typical for cells, few molecules can make it over the hump of activation energy. The hump, so like this, meaning to get to the peak. Now, the barriers for selected reactions must occasionally be surmounted. However, for cells to carry out the processes needed for life, heat can increase the rate of reaction by allowing reactants to attain transition state more often. But this would not work well in biological systems. Heat denatures proteins and kills cells. Now, heat would speed up all. Heat's not a selective catalyst, not selective enzyme, not just those that are needed. Instead of heat, organisms carry out catalysis, the process by which a catalyst selectively speeds up reaction without itself being consumed. Now, an enzyme catalyzes a reaction by lowering the energy barrier, the hump. Instead of this, it becomes this. Now, enabling the reactant molecules to absorb enough energy to reach the transition state, even at moderate temperatures, as we'll see shortly. Now, it's crucial to note that an enzyme cannot change. This is a very important idea. The enzyme here cannot change the delta G, the delta free energy. For a reaction. It cannot make an endergonic reaction exergonic. That's logical, but that's a very important idea. The enzyme doesn't provide energy. It just lowers the hump, the energy barrier. Instead of it being like this, I like the hump idea. Instead of being like this, so here the energy needed of activation is here. The thing, here, it does this. Now, enzymes can hasten reactions that would eventually occur anyway. That's the whole idea. But this enables the cell to have a dynamic metabolism, routing chemicals smoothly through metabolic pathways. Also, enzymes are very specific. They're very specific, they're very selective for the reactions they catalyze, so they can determine which chemical processes will be going on in the cell at any given time. Now, the effect of an enzyme on activation energy. Without affecting the free energy change for a reaction, an enzyme speeds up the reaction by reducing its activation energy barrier. Now, if we look at this, now this is the progress out the reaction, like let's say over time. This is free energy. Now, without an enzyme, the reaction will need higher free energy. With the enzyme, that activation energy, the hump, is lower. The difference is the same. Like, this is the free energy. That's what they mean. Like, this is G final, and here this is G initial. The shorter path of energy here is what the enzyme actually provides. It's just a shorter path. Actually, keep this. I like it. Whoa. Okay. Now, substrate specificity of the enzyme. The reactant an enzyme acts on is referred to as the enzyme's substrate. What does that mean? That means within the reaction, within the reactant here, part of the reaction, the enzyme picks a reactant, and that reactant is called substrate. Now the enzyme binds to its substrate or substrate when there are two, forming an enzyme substrate complex. While enzyme and substrates are joined, the catabolic action of the enzyme converts the substrate to the product or product. The overall process can be summarized as follows. So, enzyme and reactant it acts on means substrate, enzyme substrate complex, enzyme and product. The enzyme is never consumed, and that's it. Most enzyme names end in A's. See if you can find 3 examples in figure. In the lower left of figure 732. Where is figure 7? Figure, what the fuck? Anyway, well, now for example, the enzyme sucrase catalyzes the hydrolysis of the disaccharide sucrose into 2 monosaccharides, glucose and fructose. Now, if we look here, sucrase, sucrose, and water. Sucrase binds to sucrose and water, then each will go here, OH2 glucose, H2 fructose, and the enzyme is not consumed. Reaction catalyzed by each enzyme is very specific. An enzyme can recognize its specific substrate. Recognizes. This is even among closely related compounds. For instance, sucrase will act only on sucrose, and it will not bind to other disaccharides, such as maltose. What accounts for this molecular recognition? Recall that most enzymes are proteins. Most enzymes are proteins, and the proteins are molecules with a unique 3D configuration. So generally speaking, the 3D configuration of proteins are what drives their this emergent recognition or recognizability. of substrates to proteins. The specificity of an enzyme results from its shape. Specificity of an enzyme results from its shape. This, which is a consequence of its amino acid sequence. We've studied that before. The amino acid sequence determines the shape, the unique 3D shape of a protein, and as an enzyme, that's what provides unique ability to recognize its specific molecular substrates. Now, only a restricted region of the enzyme molecule actually binds, restricted region. Only a restricted region of the enzyme molecule actually binds to the substrate. This region is called the active site of the enzyme. It's typically a pocket, groove on the surface of an enzyme where catalysis occurs. The catalysis only occurs on the active site of the enzyme. Usually the active sites formed by only a few of the enzyme's amino acids, with the rest of the protein molecule providing framework that determines the shape of the active site. Now, the specificity of an enzyme is attributed to a complementary fit. Complementary. Actually, I'm gonna do it again. This is very complementary fit between the shape of the active site and the shape of the substrate. Shape. Now, an enzyme is not a stiff structure locked in a given shape. In fact, recent work by biochemists has shown that enzymes and other proteins seem to dance between subtly different shapes in a dynamic equilibrium, with slight differences in free energy for each pause. The shape that best fits the substrate isn't necessarily the one with the lowest energy. But during the very short time the enzyme takes on this shape, its active site can bind to the substrate. Okay, it's not necessarily related to energy. It's that this 3D shape configuration of the protein changes dynamically. It's like it polymorphs into subtly, slightly different configurations, 3D configurations, which adjusts the active site's shape in order to and within these changes, the substrate can bind to that active site. And that doesn't necessarily mean this is the idea that the lowest energy, meaning the least amount of energy needed. Because what is the purpose of the enzyme? The purpose of the enzyme is to lower the activation barrier threshold, to lower the hump, to lower the peak of energy needed by the reaction to proceed. But that doesn't govern how the protein recognizes its substrate. That's based on like empirical evidence. Whether it serves the purpose or not, it's irrelevant here. Now, the active site itself is also not a rigid receptacle for the substrate, as shown by figure 115b. When the substrate enters the active site, the enzyme changes shape slightly due to the interaction between the substrate's chemical group and the chemical groups of the active site on the side chain of the amino acids that form the active site. Now, this shape change makes the active site fit even more snugly around the substrate. The tightening of the binding after initial contact, called induced fit. Induced fit. Now, it's like a clasping handshake. Like, that's a good analogy. Induced fit brings chemical groups of the active site into position that enhance their ability to catalyze the chemical reaction. So if you look here, now the induced fit between an enzyme and its substrate. Now we have an active site here. Okay, make sure to remember that this enzyme is let's call it a living, breathing organism. It keeps dynamically changing its shape, its 3D configuration. Now, once the substrate is most suited to fit in the shape, it will bind. It will be like consumed, not consumed. It's like devoured by the protein at the active site. They fit like this in this small filling model of the enzyme hexokinase. And the active site forms a groove on the surface. The enzyme substrate is glucose. Now, once it binds to it, the what's it called? The substrate influences the active site. It affects the shape of the active site, so that the chemical groups of the substrate will have more affinity to certain groups of the active site, and the best fit will happen, which is called an induced fit. Once the fit happens, they combine, and the enzyme does its thing. Weak bonds. So we have to notice here that the bonds are weak bonds in the enzyme, inducing a change in the shape of the protein. This change allows additional weak bonds to form. So more weak bonds, causing the active site to unfold the substrate and hold it in place. To enfold and hold it in place. So that's so interesting. I mean, it's wow. Now, the catalysis in the enzyme's active site. Now, what does really happen once the induced fit is accomplished, which is the catalysis? No, the most enzymatic reactions in most the substrates is held in the active site by so-called weak interactions, such as hydrogen bonds and ionic bonds. Now, the R groups of a few of the amino acids that make up the active site catalyze the conversion of a substrate to a product, and the product departs from the active site. Now, the enzyme is then free to take on another substrate molecule into its active site. The entire cycle happens so fast that a single enzyme molecule typically acts on about 1000 substrate per second, and some enzymes are even faster. Now, enzymes, like other catalysts, emerge from the reaction in their original form. Therefore, very small amount of enzymes can have a huge metabolic impact by functioning over and over again in catalytic cycles. Because they have two objectives. First is speeding up the reaction, and this are not objectives, more like conditions, and they have to maintain their shape and form. Okay, now most metabolic reactions are reversible. Most of them are reversible. And an enzyme can catalyze either the forward or the reverse reaction. Okay, that's very interesting. Either the forward or because the enzyme captures the substrate and changes it into the product on the active site. So that active site is can accommodate the resultant, the product, or the reactant, the substrate, depending on which direction has negative energy. And we have to remember that the enzyme does not change the energy, the delta energy within the reactions. What does that mean? That means if it's negative in one direction, it will be positive in the opposite direction. But it will need less peaks. Okay, now, this in turn depends mainly on the relative concentrations of reactants. Relative concentrations of reactants and products. The net effect is always in the direction. The net effect is always in the direction of equilibrium. Now, enzymes use a variety of mechanisms that lower activation energy and speeds up a reaction. Now, so how exactly does it lower the activation energy? First mechanism. In reactions involving two or more reactants, the active site provides a template on which the substrates can come together in the proper orientation for a reaction to occur between them. Proper orientation, template. As the active site of an enzyme clutches the bound substrates, the active site clutches the bound substrates with S. The enzyme may stretch the substrate molecules towards their transition state form. Stretch substrate molecules toward their transition state form. Stressing, bending, critical chemical bonds to be broken during the reaction. So why is it important? Because stretching, increasing the distance within like the intra-atomic bonds of a molecule, and bending it make the molecule less stable and more prone to change, more prone to react. And since these molecules they have an affinity to each other, uh, they will have already reacted to each other. They will have already created the product, but bending them, stressing them, making them less stable, more prone to change, will well, will provide that function. Now, because activation energy is proportional to the difficulty of difficulty of breaking the bonds, distorting the substrate helps it approach the transition state and thus reduces the amount of energy must be absorbed. Reduce to achieve that state. Now, the active site may also, that's true, is I think that both of these are one. So can do what? This is one. Now, the active site may also provide a microenvironment that is more conducive to a certain reaction than the solution itself would be without the enzyme. For example, if the active site has amino acids with acidic R groups, it may provide a pocket of low HP in an otherwise neutral cell. Hence, here, an acidic amino acid may facilitate H+ transfer to the substrate as a key step in catalyzing the reaction. Amino acids in the active site may directly this is the third and a very important idea. They may, in the active site, may directly participate in the chemical reaction. Sometimes this process involves This process involves what? This process involves what? What's going on? This process involves brief bonding between the substrate. It is brief. And the side chain of an amino acid of the enzyme. Side chain of the AA. Subsequent steps, they have to restore the side chains to their original states so that the active site is the same after the reaction. The rate at which particular amount of enzyme converts substrate is partly a function of the initial concentration. So the main factor is partly a function of the initial concentration of the substrate. The more substrate, the more frequently they access the active sites. The more frequently they access. Now, however, there is a limit on how fast. There is a limit, which is called the limiting reactant or something like that. There is a limit on how fast the reaction can be pushed by adding more substrate to a fixed concentration of enzyme. That means the enzyme will become the limiting reactant. At some point, the concentration of substrate will be high enough that molecules will have their active sites engaged. As soon as the product exits an active site, another substrate will enter. Now, at this substrate concentration, the enzyme is said to be saturated. And the rate of the reaction is determined by the speed at which the active site converts the substrate to a product. Now, when an enzyme population is saturated, the only way to increase the rate of product information is to add more enzyme. Cells often increase the rate of reaction by producing more enzyme. You can graph the overall progress of an enzymatic reaction in the scientific skill exercise. Now, you can just look at this here. Let's do this. Okay. The active site and the catalytic cycle of an enzyme. An enzyme can convert so these are the general functions or work done by the enzyme. Now the substrate enters the active site. The substrates. Enzyme changes shape such that its active site enfolds the substrates. Now we get the induced fit. Now substrates are held in the active sites by weak interactions, hydrogen bonds and ionic bonds. Now, active site, third step is the active site lowers, now that's what it does, it lowers the activation energy and speeds up the reaction. Now we call this the enzyme substrate complex. Now, substrates are converted to products. They're converted to products within the active site, then they're released. The enzyme is back to how it were before. Now active site is available for 2 new substrate molecules. Check. Okay, just I don't know what's left for us here. After you can just go through this effects of local conditions and enzyme activity. You can just what's left? Evolution of enzymes. I don't know if this is included, but we can read through it. Now, regulation of enzyme activity helps control metabolism. Okay, allosteric activation and inhibition. What else? Localization of enzymes within the cell. Okay, there's a lot of memorizing here. And then chapter review, and that's just about it. It's a very cute small chapter. Okay, we stopped it here.